My name is Paula López. I'm part of Research and Development Department from CEMOSA, a construction and consultancy company in Spain. And well, during this presentation, as Jesus commented, I will be going into more detail into the decision support system and our developments within OMICRON project. Well, as you have seen in the previous presentation, it was about the OMICRON Intelligent platform itself. This platform has its own decision support system model. And you can see here in the scheme of the right a bit of the context on how our developments fit within the whole project. Well, the data from the demonstrator is introduced within the OMICRON Intelligent platform on the digital twin layer. And this layer is closely interconnected with our decision support tool. This decision support tool is, it aims at reducing the volume of interventions, the maintenance costs, and the hazardous situations, as well as making more available the network. And is itself formed by two different modules. The one that I will be presenting in this presentation, which is the infrastructure condition, which outputs will be also used in the second part of the decision support tool, which is the asset management plan optimization, which will be presented by Alice in the next presentation. It's also important to comment that the infrastructure condition will analyze two different assets. The first one is pavement condition analysis, and the second one will be bridge condition analysis. So we can start by pavement condition analysis. The objective of this analysis is to apply machine learning techniques on historical data in order to predict and analyze the condition of pavement. Well, the idea is that this prediction standalone visualizing the platform is useful
Paula,
for the...
Paula, sorry, stop.
Yes.
Sorry, mute the microphones. Mute the microphones, please. Paula, continue.
Okay, thank you. So it can be used standalone in the platform, so decision makers can make informed decisions on the maintenance, and as well will be used within maintenance planning algorithm as key parameter. The scheme shows this workflow, and we have historic records. We make the prediction models, in which we predict the parameters of the road. These predictions are used to assess the condition of the road, and they are both used for OMICRON Intelligent platform and for the maintenance planning. Well, now we will go briefly over the methodology applied for this analysis. The first step is the data preprocessing and exploratory data analysis. Whenever we're working with data-driven techniques, there is a process, an internal process with the data for analyzing and managing the available data. The raw data is received and stored and preprocessed to obtain adequate and efficient structure to work with. And also exploratory data analysis is also an essential step to analyze everything that is available. In this case, we get information from inspections, in this case, International Roughness Index, site force coefficient, and texture indexes. And the next step is the data process. In this step, which is an extensive one, there is a series of data science methodologies that need to be applied on the data, and that I won't enter much into detail, but are related to the evaluation and parameter selection, the data structuring, rounding, outlier analysis, missing values, and feature selection. The next step is the approach and model selection. Well, in this way, there are different ways of constructing the models in relation to which parameters are introduced, how they are interconnected between them, the different time steps that can be selected. And each one of these ways of doing it is what we call approaches. In this analysis, we've tried 5 different approaches. Besides this selection, also after exploratory data analysis is performed and we understand the quantity and the quality of the data, different models can be applied. In this case, a linear regression model, decision tree, and random forest are analyzed. And in the end, the model and the approach which provides the best results will be the selected methodology. The following step is the model execution and evaluation. Once the model and the approach is selected, then we need to execute the algorithm. Here we follow the diagram that you can see on the right. The available data is split between trained and test datasets. The trained dataset, which is 80% of the data, is used for the model fitting. In this case, the hyperparameters are tuned for the specific model, and this fitted model is used for the prediction, which uses the remaining 20% of the data. With this trained model and the test data, we get the predictions. And since these predictions use test data that wasn't used for the training, then it's suitable for evaluate the model in an adequate manner. After that, we go to the condition assessment step. In this case, now we have the predictions from the pavement parameters, but we want to have a value which tells us how good the pavement is. For this, we apply cost action 354 to estimate a global performance index that will give you a value, a numeric value that will tell us how good the road is based on this prediction. And finally, we have the maintenance algorithm connection. In this case, well, the pavement prediction is based on its input, which is inspection results related to data points. We need to work with that to provide more adequate structure, which is small segments that can be used by any type of algorithm, any kind of optimization, and any type of methodology that this or any other company may want the outputs to work with. Here we can go briefly on the results and conclusions. Of course, all the 5 previously approaches, all the models are executed, and then the best results is provided by random forest algorithm, and also the approach on the right, where you can see how the different input variables and outputs are connected. This model and this methodology provides an output of a mean absolute percentage error of 5.6%. Just to summarize, on the left figure, you can see an example of one of the decision trees from one of the random forests that is used for one of the predictions. As conclusions, well, 2024 road parameters data and road condition indexes are predicted for the road and is integrated within OMICRON's platform as a standalone feature and used within the DSS. You can see here, I mean, our partners already showed the overall platform, but we thought it would be interesting for you, now that you understand the algorithm, to see the results. On the GIS, you can see different colors showing the state of the road. And on the left side, you can see the different parameters and predictions for the indexes and the parameters in different tables and different graphs. This global methodology is designed to be modular, allowing for adaptability, transferability, and kind of easy modification. As you can see, well, new years can be included if they're available, new possibilities if new data from other assets is available, and it can also adapt to other models. Now let's go to the second asset to be analyzed, in this case, bridges. To provide some context, as a structure age and approach the end of the service life, it's essential to prevent and to make maintenance actions which are more preventive. The figure on the right, in the top, shows the evolution of the number of collapses of different assets with time, and you can see the increasing trend. And in the graph on the bottom, you can see the number of publications of different analyses that are part of this analysis, which are damage identification, structural health monitoring, and operational model analysis, how this number of publications increased over the last years, especially structural health monitoring. Within this context that we are mentioning, this project presents the assets of the condition of the Sette Bridge, the demonstrator in OMICRON project. Here you can see the blueprint, some figures and some models where you can see also the accelerometers presented in the bridge. This case of study is really interesting due to its service life, a bridge with over 50 years, and some specific parts that are interesting to analyze, like the Gerber connections and a structural steel that has lost its protective cover. This slide shows briefly the workflow of the structural health monitoring applied. As you can see, the first step that is covered is the operational model identification of the bridge using the information coming from the sensors, resonance frequencies, mode shapes, damping ratios. Once these model parameters are calculated for the different time series signals, then it is necessary to remove the environmental and operational variables and to provide the damage identification and damage detection techniques. Simultaneously to this analysis, a finite element model is created and is updated, taking into account the geometry, the materials, and the boundary conditions of the actual bridge. The continuous updating of this model is the one that will provide the structure stiffness in different areas. I will present all of these parts of the analysis in more detail now. As I commented on the first step of the identification, which is the baseline dynamic properties are obtained using a time domain technique. In this case, the model properties obtained are shown in the right side with the 8 modes, which are relative to 8 different frequencies and damping frequencies. This first baseline dynamic properties identification is performed, then this is done for all the signals of the monitoring period. The results are statistically analyzed, and as you can see on the bottom part of the graph, they are also clustered. This means that in the end, we will have the evolution of the different model parameters with time. And as you can see, they are clustered with different colors. The next step, as we mentioned before, we found different day-night cycle, repetitive manners within the data. This shows that there are some external environmental factors that are not useful for the structural analysis that need to be removed. For this, correlation analysis between the independent environment variables and identified properties are analyzed. The air temperature is selected as the proper feature to remove these kind of effects. And the methodology that is used to remove this effect is multiple linear regression model. In the left, you can see both. You can see for 3 of the frequencies identified over time. You can see how in blue the experimental data is showcased and the output from the MLR model. In the zoom, it's easier to see the trends that we mentioned before that needed to be removed. To identify the damage, a control chart based on Hoteling's T-square is applied as a novelty detection technique. In the figure in the right, you can see how data from November to July is used to train the chart, and how from July till September is used for the testing. The thresholds are defined, and even though these thresholds are punctually overpassed over the whole training period, there is an increase in the test period. This result this is one of the conclusions of this analysis that shows a minor loss of stiffness for this type of bridge, and this showed in the image. Simultaneously, a finite element model, which follows the geometric properties, material characteristics, and boundary conditions of the model, is developed and is calibrated with sensor data. Once this model is correctly calibrated, a meta model is used for the continuous updating, which provides the stiffness multipliers as outputs. As no real data from a damage can be accessed through the monitoring system, then synthetic damage scenarios are generated. These synthetic damage scenarios are inserted within the model, and after the trial, it can be seen that the damage can be both identified and located. This can be seen here in the graph, where the training period is shown, and for three of the stiffness multipliers for 3 different zones. And when the damage scenario is inserted, even though the 3 areas suffer some variation, it is only in the area with the real damage that the system finds the damage. As a complementary analysis, as of verification step, data from strain gauges is used to confirm the results from the previous analysis. Anomaly detection is applied, this time using a neural network, and the results that are shown in the right in the graph, where the anomalies are marked in red, shows that these anomalies align with the results from the control chart that I previously showed in the previous slides, within the site with the span-Gerber connection. Well, some key conclusions. The dynamic properties have been estimated and analyzed over time. Synthetic damage scenarios have been simulated, and time domain structural health monitoring conclusions have been validated with the anomaly detection for strain gauge analysis. Here again, you can see the results from this analysis within OMICRON platform, showing the BIM model, the results in this slide, in this part of the interface about the dynamic identification. But you can see also the evolution of the parameters with time, which is easy to interact with. And finally, the damage detection graphs. Okay. Well, aligning with OMICRON platform and with the development I just showed, from CEMOSA, we have developed our own digital twin-based platform, which is Tembox, which already comes with a series of monitor assets and scenarios. In this slide, you can see 4 examples of the capabilities of the platform. The first one is oriented to bridge monitoring and analysis and shows the GIS BIM environment visor, and is in connection with a series of analysis of the bridge structural health monitoring, really aligned with OMICRON platform. Here you can see the analysis of the model identification, the evolution with the parameters with time, and the location of damages in a comprehensive, user-friendly, and interactive way. The second example also related to bridges, but in this case, it was requested to be more focused on inspection. So in this case, you can see the BIMGIS environment, the results from inspection, and some defects being introduced within the BIM model. So as you can see, it is also it's useful to insert inspection information from the platform itself. Other assets, for example, in the third example, there is the landslide monitoring, which allows the access to real-time data from IoT sensors. There is a series of analyses and alarms prepared to assess the condition. Finally, the last asset is one relative to pavement. We show a GIS interface showing the condition of the different parts of the pavement. So as a conclusion, this was the infrastructure condition with decision support system scope, which aims to promote the shift into predictive maintenance. As really clear conclusions, pavement historic data has been used to predict pavement condition. Bridges monitoring data has been used to analyze bridge condition. Infrastructure condition outputs are interconnected with the DSS algorithm, and results are integrated within OMICRON's intelligent platform. That will be all from my side.